Welcome to the second movie about YASARA on Android. This one provides detailed usage instructions and, as a practical example, shows how to visualize a protein's electrostatic surface potential with a Poisson-Boltzmann calculation. The gadget in this movie is the world's first Android tablet with Intel CPU, the Ramos W32. It features 1GB RAM, a hyper-threaded 1.6 GHz Atom CPU and a Power VR GPU. Everything I'll show you works exactly the same on Android smartphones. The touchable user interface is the same as on Windows 8 tablets, and there's another video covering those, so I'll quickly walk you through the most important features. You can zoom the interface to make sure that all the widgets have the size that best fits your fingers. And the interface is fuzzy, so YASARA activates the closest option, even if you missed it. Here I tapped Options, Input Devices, Virtual Keyboard Parameters to configure the virtual keyboard, change its size and transparency. And at Options, Input Devices, Virtual Keyboard Layout, you can choose your favorite keyboard layout. Over 60 are available. To show the virtual keyboard, tap on the left side. This is not one of those stripped-down keyboards that pretend to be smart but are always lacking the key you need. Instead, everything is where you expect it, like the function keys that change the scene style. You can work with YASARA normally while the keyboard is visible. To make it disappear, press the Hide key up here. If you already know in advance that you only want to press a single key, tap on the right side. Then the keyboard will disappear again right afterwards. Now I'll show you the gestures. Hold down a single finger to rotate around the X and Y axes. Use a swipe gesture to spin. If you now add a second finger, you can additionally translate along the X and Y axes. Alternatively, if you tap and hold two fingers at the same time, you can use the well-known pinch gesture to translate along all three axes and rotate around the Z axis. If you now add a third finger, this finger rotates around the X and Y axes. So with 3 fingers, you got access to all 6 degrees of freedom. Tap on an atom to mark it and display its properties in the head-up display on the left side. Hold down the finger without moving it to enter the context menu, for example to color the residue. A faster but more difficult alternative is to tap with 2 fingers and the marked atom in between. And now a helpful trick. Even if the virtual keyboard is hidden, the bottom key row is active. So you can hold down the Control key and tap on additional atoms to measure distances, angles and dihedrals shown on the left. Or you can hold down the Alt key to repeat the last command, coloring residues in this case. Or you can press the Space key to enter the command console, where analysis results are shown. Now let's use all that to actually do something. I promised you a surface colored by electrostatic potential. One thing to note about surfaces is that YASARA calculates them in real time. So I load a protein, crambin from plant seeds in this case, and show a molecular surface also known as Connolly surface. As surface color, I choose the color of the closest atom on the outside. I make it a bit transparent, and for the inside I choose green. If the atom coordinates change, for example during a simulation, the surface adapts immediately. Just for fun, I run a macro that swings the side chains around. And this runs even more smoothly if I go to View, Show Surface, Parameters, and let YASARA calculate the molecular surface with a Gaussian approximation. Concerning the electrostatic potential surface, I'll simply show you part of a YASARA tutorial that explains the details. In YASARA, electrostatic potentials can be calculated in 2 different ways. The first uses the particle mesh Ewald method, which considers periodic boundaries and works with a uniform dielectric constant of 1. You could, for example, use this one to calculate electrostatic potentials during an MD simulation in explicit solvent, and then average the results. The second approach is based on the Poisson-Boltzmann equation, which permits to calculate the electrostatic potential with implicit solvent. Different dielectric constants can be assigned to solute and solvent regions. The latter may also contain implicit counter-ions. You can set these parameters by clicking Analyze, Energy, Solvation Energy Parameters. The default dielectric constants are 80 for the solvent and 1 for the solute, but depending on the application, it's common to increase the latter, for example to 4. Time to load another protein. I choose PDB file 2SOD, a crystal structure of the enzyme SOD, superoxide dismutase. SOD provides antioxidant defense in most cells by turning 2 superoxidized anions into hydrogen peroxide and oxygen. To catch the negatively charged superoxide, a positive funnel leads to the active site, which is built around copper and zinc ions. Let's visualize this funnel. All calculations are done in the cell, so I define one which is 10 angstrom larger than the protein. Next, I click Edit, Clean, All to ensure that the protein is in a clean state with all hydrogens present so that charges can be assigned. Then a force field needs to be selected. I pick Amber 2003. The various options here don't really matter now, since we just need the charges. And finally, time to show the surface. Again, a molecular surface, and as surface color, I pick ESPPBS, which is just an abbreviation for Electrostatic Potential from Poisson-Boltzmann solver. Now we need to wait a bit. YASARA outsources the task to APBS, the Advanced Poisson-Boltzmann solver, another great open source tool distributed with YASARA. Visit www.poisson-boltzmann.org for more details. The color code is blue for positive regions and red for negative ones. And not surprisingly, the most bluish region on the surface is the funnel that leads to the active site, where the superoxide anions are caught. Many thanks again for watching. Please get your YASARA boarding pass from www.yasara.org. And don't miss the many interactive tutorials which you can find in YASARA's help menu. For example, this one about running accurate simulations in water.